Welcome to our tutorial on fine-tuning the cutting-edge Gemma 2 open-source model. Today we'll explore how to customize this AI powerhouse for your specific needs using tools like Huggingface and Unsloth, which integrate seamlessly with Gemma 2.
Fine-tuning models is something real cool, 'cause off-the-shelf models got you looking like a fool. But we'll keep it simple, you know that's true. By fine-tuning models, the power's with you.
In fine-tuning dozens of models, we found this to be the easiest, most approachable fine-tuning method. We'll start our journey at the Unsloth GitHub page, where we'll find a ready-made Jupyter notebook. While we'll make some adjustments along the way, this notebook provides an excellent starting point. Unsloth, for those unfamiliar, aims to democratize fine-tuning and inference with powerful libraries and services. Our fine-tuning process will take place in a Jupyter notebook on Google Colab. We'll use Unsloth's libraries to harness the open-source Gemma 2 model, and once we're satisfied with the results, we'll upload our fine-tuned model to Huggingface. You'll have the option to keep your model private or share it publicly on your profile. Before we dive in, let's check our runtime environment. We'll be using the latest version of Colab with GPU accelerators. If you're using a paid version of Colab, you'll have access to more powerful options like TPUs and A100s. For this tutorial, we'll opt for an A100 to give us more memory headroom. It's worth noting that using these resources comes with a cost. That said, 100 compute credits is only $10, and we only use a little under 10 compute credits with the demonstrated setup, so even if you're doing 10 times longer training, you should be in single-digit US dollar territory. The libraries and model we'll be using are entirely free. You can try the tutorial with cheaper compute options as well. T4s, for example, are often sufficient. Now let's set up our data. We'll drag and drop our own dataset directly into the notebook. I'll provide this data in the video description so you can follow along. We ideally want hundreds or more of examples, but a few examples will be fine for our demonstration. Next, we'll configure our model. We need to decide on the maximum sequence length and choose which model to use. We'll be using 4-bit quantization to reduce memory usage, which will help our models run efficiently on GPUs. You have two main options depending on the size of the model you want to use. The 9 billion parameter model might work well on cheaper GPUs, while the 27 billion parameter model may require something more powerful, like the A100 we're using. In this tutorial, we'll be fine-tuning our model on stories and their associated summaries. Each story in our dataset is quite lengthy and comes with a corresponding summary. Our goal is to teach the model how to summarize stories in our specific style. An important parameter we need to consider is the maximum sequence length. This determines the maximum size of our input and output texts. We want to be careful about setting this value because we don't want examples that exceed it. For instance, if we have a very long story, we wouldn't want the model to summarize it by only considering the last few paragraphs. To ensure we're setting this value correctly, let's calculate the lengths of our stories. We'll use a tokenizer to count the tokens in each story. We'll deliberately leave one story out of the dataset to use as a test case later. Let's start by using the 9 billion parameter model, which is more cost-effective and easier to run. This should be the starting point for most of you. You can always move up to the 27 billion parameter model if you need it. After running our token counting code, we can see that some of our longest stories stretch up to about 16,000 tokens. Given this information, let's set our maximum sequence length to 16,384. This gives us a little buffer over our longest story, allowing space for both the story and its summary. Now, let's look at the LoRA adapter configurations. When we talk about updating only a small portion of the parameters, we mean we're only going to fine-tune these adapter layers. This is a common method in LoRA-based fine-tuning approaches. Instead of changing all the weights in the base model, we're just adding some weights to the end to fine-tune effectively. The two main values to consider here are R and alpha. The R value represents the size of our adapter layers. We're using a smaller option, but if you have complex fine-tuning needs, you might want to increase this to something like 32. The alpha value is a weighing parameter that determines how much we should prioritize the new data versus the knowledge in the base model. If you want your model to be very stylized and diverge more from the base model, you might want to increase this alpha value. Next, we need to prepare our dataset. We'll create a list of fine-tuning examples, each consisting of a prompt that includes both the story and its summary. During fine-tuning, we'll provide both the story and the summary as examples for the model to learn from. Later, when we use the model, we'll only provide the story and ask it to generate the summary. Let's create our list of fine-tuning examples. For each story in our dataset, we'll create a data point that includes a text field for training. This field will contain our prompt structure, which includes an instruction, the story, and its associated summary. We'll also add an end-of-sequence token to signify where the model should stop generating. After creating our dataset, it's a good idea to print out a few examples to ensure everything is formatted correctly. We should see our instruction followed by the story and then the summary. Now we're ready to move on to the exciting part, training our model. There are a few important concepts to understand here. First, let's talk about the effective batch size. This is calculated by multiplying the per-device trained batch size, the gradient accumulation steps, and the number of devices we're using. In our case, the effective batch size will be 8, meaning we'll train on 8 examples per step. Using heuristics and effective batch size, you can calculate a desired number of training steps. That said, an epoch specification, which is the number of full passes through your data, might be an easier option. Also, if you have many training examples, perhaps in the hundreds or thousands, you can watch the loss as the model trains and then stop it when the loss is leveling off. That is, when additional training isn't meaningfully improving the model. Let's start the training process. Don't be alarmed if you encounter an out-of-memory error on your first attempt. This is common, and we can adjust our parameters to fit within our available GPU memory. I would recommend adjusting training configurations like the batch size and gradient accumulation steps, and then tweaking the context window length if necessary. Third time's a charm, and with our working configuration, we're using about 30 gigabytes of memory for training, which is about 80% of our maximum available memory on the A100 GPU. The context window, max sequence length, has a significant impact on memory usage, so adjusting this can help if you're running into memory issues. Once the training is complete, we can move on to testing our newly fine-tuned model. We'll use our prompt format to generate a summary for a test story. For simplicity, we'll use a hard-coded story for this example. We'll set the max new tokens parameter to a high value like 512 to give the model plenty of room to generate a summary. Let's examine the output. We should see our instruction, followed by the input story, and then the generated summary. If everything worked correctly, the summary should reflect the style and approach we trained the model on. The final step is to save our fine-tuned model. We have two main options here: saving locally or uploading to Hugging Face. Local saving will preserve the model on your machine, while uploading to Hugging Face allows you to share your model with others or use it in various workflows. In saving our model, we have a choice between saving just the LoRA adapters or the entire fine-tuned model. Saving only the adapters results in a much smaller upload, but it means you'll need the base model as well to use it later. For production-grade hosting, you might want to consider using a system like VLLM, which is compatible with both published saves and file-based saves. For this tutorial, we'll focus on saving the entire model in Float16 Precision for VLLM compatibility. To save our model to Hugging Face, we need to set up our credentials. Let's head over to the Hugging Face website and navigate to the Settings page, then to Access Tokens. Here, we'll create a new token with write access. Make sure to keep this token secure as it provides access to your Hugging Face account. Now let's give our model a name. We could call it something like Gemma 2 Summarizer LoRA. Use the private upload argument if you don't want your model publicly available on Hugging Face. The process of uploading to Hugging Face might take a few minutes, depending on your internet connection and the size of the model. Once it's complete, you should be able to see your new model on your Hugging Face profile. It will come with a default README file, and it's ready to be integrated into various workflows. The code snippets we used for the dataset creation and token counting will be available in the video description, along with the diagram file. Feel free to adapt these for your own projects. I'll be keeping an eye on the comments section, so if you have any questions or run into any issues, please don't hesitate to ask. Thanks for watching, and please enjoy responsibly.